Hello, my plant friends. This is Professor Beams from ECC coming at you. Today, we are going to do a real quick lecture about water, how the water cycle works. We're going to talk about how water molecules work, and we're going to talk about surface tension and capillary action. This is important in the field of plant and soil science because water is a critical component of the soil system, but that's largely to feed the organisms that live in and on top of the soil system. And so that's going to be our arthropods, our microorganisms, and very importantly, plants. So plant cells are largely water. When a plant is fully filled up with water, we call that turgidity. It is a turgid plant. So plants don't have bones or a skeletal system the way that, humans and animals do. So what we have is we've got this sturdy, stiff structure that holds all of our soft tissues up. Whereas plants, they have cell walls that are made of carbon. And then when you fill those cells so that the walls expand all the way out with water, a plant stands upright. So in the first thing in the morning, a well-watered plant is going to be standing upright. Let's see, let's look at this one. This is a happy, well-watered house plant. So the leaves are nice and shiny, even though they're a little bit dusty. They're nice and shiny. They're nice and full. If a plant starts to become water stressed, or here in Texas, towards the end of the day for during the hot season, plants will pull their water out of their above ground leaves where water can be lost very regularly and pull that down into the root system, back into the woodier parts of the trunk. And so the leaves up top will start to wilt. They will become less shiny and lustrous, a little bit more dull or gray in color. That's a water stressed plant, or a plant that is conserving its water resources by drawing water out of the leaves. So water is a very important component to plants. So I think I use this set of slides in almost all of my classes in one form or another. So let's go ahead and look at the water cycle. So maybe we haven't thought about the water cycle since we were in grade school, but there is a water cycle on the planet. And so if we start at the top, very literally, there's water in the atmosphere. When water droplets condense, they form clouds. When the clouds become very dense and very full of water, it will reach a capacity where it can no longer hold, and then that water will fall in the form of precipitation. So precipitation includes snow and rain and sleet, wintry mix. Any water falling from the sky is precipitation. So a few different things will happen with that precipitation. Up high altitudes in the mountains, we will see accumulation. So that's snow drifts, ice, glaciers, things like that. That over time, those elements will melt, and as they melt, they move with gravity. They, being the water molecules, will move with gravity down and find their way either into the water table or into a body of water, streams and creeks that then join up with larger rivers and lakes and eventually move into a large body of water, such as a large lake or the ocean. Or over time, like I said, they will seep down through the soil into aquifers and become part of the water table. So, as water flows down, they interact with water molecules, interact with plants. And so plants will take up the water and assimilate water molecules into their cells and into their tissues. Um, Water will then be returned to the atmosphere in the form of evaporation, both from the surface of the earth as well as through evapotranspiration. So that is the effect of a plant transpiring water through its system and then out through the stomata of its leaves, from which it will evaporate into the atmosphere. Again, that is evapotranspiration. Um, then we have, if we go down towards the lower part of this graphic, the lower part of the water cycle, um, water is soaked into the ground, it percolates in, um, it will make its way into the ocean where we have something that I always forget is happening is there's volcanic activity on the ocean floor. And that will force steam up and back out into the atmosphere. This fun fact that we need to remember is the ocean contains 97% of the Earth's water. Um, and then it will evaporate back up into the atmosphere. It will rise and condense into clouds. And there, my friends, we have the water cycle. Now let's look at the individual water molecules. So water is a unique molecule, as most of us know, H2O. That means it has two hydrogens and one oxygen that create a single water molecule. Water molecules are polar molecules. They have polarity. That means that one end of the molecule has a negative charge, that would be the oxygen, and the other end of the molecule has a positive charge, and that's going to be the two hydrogens. So we see that here in this graphic that the O, the oxygen, has a negative charge, and the hydrogens have positive charges. Now, the nature of this molecule is that it is not a stable molecule. It is continuously seeking other molecules to create bonds with in order to find an equilibrium and stabilize. So, in order to do that, each oxygen wants to bond with four hydrogens. It already has two of its own hydrogens, which means it's looking for two more. Each hydrogen wants to bond with two oxygens. It has its own oxygen already, as we can see, but then it wants to bond to a second one. So what we find is each individual water molecule is seeking four other water molecules to bond with. Two of them are going to provide hydrogens and two of them are going to provide oxygens. So here we find this effect where water is always looking for the next bond, right? Well, what if we have a finite amount of water, just like this bead of dew that we have here in this graphic? There's a finite amount of water, and there are no more water molecules to bond onto. What happens is the top layer creates double bonds that you can see on the left-hand side of the screen right here. So here at the surface, we have two bonds between each molecule instead of the single bonds that we have below. And that creates surface tension. So um, when I teach this lab in person in the classroom, we always do one of my favorite activities that I remember doing from grade school, which is everybody would get a fresh, new, clean, shiny copper penny and a dropper and a cup of water. And then we would all take bets on how many drops of water do you think that you can fit on the face of the penny. Guesses would usually range from like 5 to 15. The highest I've ever seen from a very, very determined and careful student was 38. 38 drops of water on a penny. And that's because once the face of the penny filled and got wet, those drops of water started to stack on top of each other and they rose higher and higher and higher until the surface tension finally broke and water splashed down on the surface of the table off of the penny. So, um, here's where I like to draw a little graphic. Um, the surface tension becomes, and I'm going to stop my screen share so we can see this entire whiteboard. So the surface tension is a matter of ratios. how many single bonds to how many double bonds. So right here, I drew um, a bead of water that only has nine individual molecules in it. So all of the outside molecules are going to be double bonds, like so. And all of the inside molecules are going to be single bonds, like so. So if we look at the single to double bond ratio here, we have 1, 2, 3, 4 single bonds to 1, 2, 3, 4, 5, 6, 7, 8 double bonds. That means we have a 1 to 2 ratio of single bonds to double bonds. We have literally twice as many double bonds as we have single bonds. Now, let's say we have a much larger drop of water with 1, 2, 3, 4, 5, 6, 7. Um, I'm going to go ahead and make 7 rows of 7, and I don't know why I chose 7. And I'm going to end up having to do some quick math, or we can do a little bit of an estimate. So if we have 7 rows of 7, clearly we have many more, um, we have many more individual molecules here. All of the outer bonds are going to be double bonds versus the inner bonds are going to be single bonds. And without going through and drawing each individual one in, and without going through and counting each individual bond, I can tell you there's going to be 1, 2, 3, 4, 5, 6. 6 double bonds on this outside times 4. So that's going to be 24 double bonds. Two, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So that's 5 plus 6 is 11, and we're going to have that 1, 2, let's see, 1, 2, 3, 4, 5 times 11 times 5, so that's 55 to 24. My math might be just a little bit off, and if somebody wants to correct me in the comments, oh my gosh, please do. I'll update this video. But instead of having twice as many double bonds as we have single bonds, in this one, we have twice as many single bonds as we do double bonds. So the surface tension is going to be significantly higher in a smaller drop of water versus a larger drop of water. Now, compare that to a pool of water or an entire ocean. The surface tension goes way down. But when we think about it in terms of soil water, the number of individual particles that can bond together around a single grain of soil, we're looking at a very small number of molecules and a very high amount of surface tension. Okay, back to the slides. So, um, surface tension is part and the double bonds and the polarity all go into capillary action. So, capillary action is the effect that you get when you have a dry beach towel on your chair at the pool, but the corner dips down into a puddle next to your chair. And after a little while, that entire puddle will wick its way up through the fibers of your pool towel. Capillary action is the effect where water molecules will spread and expand against the forces of gravity. So, in this graphic that I have right here, it's a very crude uh, image of two glasses, one full of water, one that started empty, and then we have a fibrous material going from one glass to the other. So this is another lab that I will do in person with my classes where we'll get a full glass, we'll get an empty glass, and then we'll get any fibrous material. A rope works. Sometimes we'll just grab a paper towel out of the restroom and twist it up and then put it between the two cups. Water will move up through the fibrous material and drop down into the empty glass until the two glasses have an equal amount of water in each of them and they have reached equilibrium. That is capillary action, water moving through fibrous material against the forces of gravity to reach an area that has less water in it. And this is how it works in plants. So we see water down at the bottom will be absorbed by the roots. It moves into, through osmosis, it will move through the membrane of the tiniest, most succulent little plant root hairs. It moves up into the vascular system. Things that move up in the vascular system of a plant are moving through the xylem. Nope, that's xylem. It moves up through the xylem and through capillary action will move up into the different parts of the upper plant, and then water will evaporate out of the stomata on the leaves. And again, that's evapotranspiration. So that is just a really, really quick overview of water and how it's important and why it happens. And this piece of information is relevant whether you're taking my botany class, your green garden management class, your intro to soil science class, the irrigation design class. All of it is important. We need to know how water works to know how it works within a specific system. So thanks so much. I'll see y'all next time. Bye.